Okay, so AsynPortDriver is a C++ class, base class for writing asyn port drivers. As you just heard, asyn is this standard interface between device support and the driver. And as I said, I think you should use asyn to write all Epic's device drivers, not just asynchronous ones, with the exception that you should use stream device if you can. So what is AsynPortDriver? It's a C++ base class that considerably simplifies the task of writing an asyn port driver. It was initially developed as part of area detector, but it was moved back out of area detector and into asyn itself quite a while ago, back in asyn 4-11. We're now up to 425. All of my area detector, D to A, binary I/O, and most recently motor drivers now use AsynPortDriver. And the drivers in the next part of the class that we're going to do this afternoon use AsynPortDriver. So it hides all the details of registering the interfaces, registering the interrupt sources, doing the callbacks, and default connection management. So why was it written in C++? Because I wanted to do a number of things that are harder to do in C. The first is inheritance. So we want to have virtual base class functions that might implement a useful behavior, but that you can override if you want to change that behavior by doing some enhanced capability in your derived class. And then importantly, particularly for area detector, was the ability to have template functions. So template functions is you write a single function that can handle any data type. And that's used extensively in area detector, which for the ND arrays, there's 8 possible data types. And you want to have one function that you just write once, and it can handle any data type. So the capabilities in AsynPortDriver, one of the important things that it's got is a concept of a parameter library. So drivers typically need to support a number of parameters that control their operation and provide status information back to their clients, device support. Most of those parameters can be treated as int32, int32 digital, float 64, or strings. The exception here really being the generic pointer and the arrays are not handled by the parameter library at present. So typically what happens is some new parameter arrives from, say, an output record, or new data arrives from the device. You want to change the value of one or more parameters in the object. And then for each parameter whose value changes, you set a flag noting that it has changed. And when you're all done, you want to call all the registered callbacks for every parameter that got changed. And this is a common sequence of operations that most drivers need to do, and so we try to make that easy. So AsynPortDriver provides methods to simplify that sequence. So every parameter is assigned, it's very simple, just assigned an index, an integer number, based upon the string that's passed to the driver in that driv user interface that we've already talked about. So AsynPortDriver has a table of these parameter values, and in that table there's an associated data type and an asyn interface, and it caches the current value and maintains a flag that says whether it's changed or not since the last time callbacks were done. There's a separate table for each asyn address that the driver supports. So if it's a 16-channel ADC, then there are separate tables for each channel of the ADC. So drivers use AsynPortDriver methods to read the current value from the table and to set new values in the table. And then there's methods to call all the registered callbacks for values that have changed since the last time that callbacks were done. So an AsynPortDriver constructor looks like this. You give it so that your derived class calls the base class constructor with the name of the port, the maximum number of addresses that your driver is going to support, the maximum number of parameters that your driver supports, a mask, a bit mask of all the interfaces your driver supports. int32, float64, octet, driv user, and so on. Another bit mask, which is all the interfaces on which your driver wants to be able to do callbacks. A set of flags, these are the ones that we've seen before, you know, asyn can block, asyn multi-device, an auto connect flag, a priority, and a stack size. The things that we've seen before that get passed to asyn manager. So these are all those things I just said. And based upon these arguments, the base class constructor takes care of all the details of registering the port driver, registering all the asyn interfaces, registering the interrupt sources, and creating the parameter library. You just make this call, and all the rest happens behind the scenes. AsynPortDriver has the following parameter library methods. In your constructor, you have to call create parameter. You give it the name of that parameter. That's going to be the driv info string that records use at the end, like binx back in that example. A parameter type, is it asyn int32 or float64? And then you pass it the address of an index that create param is going to assign an index number to this parameter. Then you've got set integer param, and there's two syntaxes for that, two different calling protocols. If the more general one is you give it which list, so this is the address, the index is which parameter, and the value. But if you omit the list, it defaults to list 0, address 0, because many drivers only support one address. Same thing for double, set double param, set string param, get integer, get double, get string. And then there's call param callbacks. If you give it no arguments, it defaults to just doing the callbacks on address 0. If you give it an address, you can do callbacks on other addresses. So there are methods to read and write values to do these are the parameter to set the values, get the values from the parameter library, do the callbacks when parameters change. Then there are methods that are called when an asyn client writes a new integer value or wants write int32 or wants to read an integer value or a floating point value or an octet value or a 16-bit integer array, read or write, and there's a method to do callbacks on arrays. So these are the methods that device support calls to write a new value from an output record or to read a new value for an input record. The base class implements, for instance, read int32 to just return the value from the parameter library. And that's often sufficient. That's all you need to do. So you often don't need to implement the read functions because the base class function does what you want. It just means that if the record is, scanning at 10 hertz and reading the value, it's just going to get the latest value from the parameter library. As long as your driver did write set int32 param, you don't need to implement the read int32 function unless you really need to do something when that read operation is done. When that read function is called. So the base class typically takes care of everything for the read functions. You do need to implement the write methods if any immediate action is needed on a write. Otherwise, you can use the base class implementation, which just stores the parameter in the library. But if when somebody calls write int32, you want to push a value to the hardware, then you need to implement the write int32 function. But it's a virtual function, and you're replacing the function that's in the base class. So there's an example in asyn that's called test AsynPortDriver, which is a digital oscilloscope simulator, very simple. You can set the range for the vertical axis and an offset for the vertical axis. And it's a kilohertz sine wave. You can throw some noise on it, turn the scope off and on, set the time it's going to update and the number of seconds per division on the horizontal axis, and a trigger delay. It gives you back some statistics on the min and max and mean, and you can control whether the waveform record here is I/O interrupt scanned or periodically scanned. So there's 18 records in the example database. All the input records are I/O interrupt scanned, so they're scanning whenever the simulator produces a new value for those records. For those parameters, those corresponding input records are I/O interrupt scanned. The waveform can be switched to either be I/O interrupt or periodic. This whole example is 340 lines of well-commented C++ code. So, this is a good example to look at as an example of how to write a driver. It doesn't actually communicate with any hardware, but you can see it's pretty clear where you would insert the code there to actually talk to a device. And we're going to go through an example of this afternoon with the measurement computing device. So the database looks like this. Here's the record for time per division, and then there's a time per division underscore RBV. So that's a readback value that shows you what the actual time is. This is an analog output record that's not periodically scanned. It's just scanned. This record processes whenever you type a new value, enter a new value, and this analog input record is I/O interrupt scanned. So anytime the value changes for whatever reason, this record will process. The device type is AsynFloat64. This is that syntax for the input and output link that you've seen with the deriv user field here. And this is what the constructor for that looks like. So it takes a port name and a maximum number of points, and then it calls the constructor for the AsynPortDriver base class, passing the name of the port. This only supports one address. The number of parameters are computed lower down or computed in the code. This is the mask of interfaces that it's going to support: int32, float64, and float64 array, and deriv user. So those are the 4 interfaces this driver supports. These are the 3 interfaces that are supported for callbacks, because we don't do callbacks on the deriv user interface. We set this flag to 0 because it does not block and it's not multi-device, so that flag is 0. It does auto-connect, and we set the default priority and stack size. We define some symbolic constants, and typically this should be done in your header file, your .h file, because this is basically what you're publishing about the capabilities of the device. You're telling, this is sort of your contract with the clients, is that these are the names of the parameters. Your contract is not what is the value of the PASYN user reason field, because you want to be able to change that. But what you don't change is these strings. So you put these strings typically in a header file, but you define them as symbolic constants, which you can then use in this call to PASYN manager, AsynPortDriver's create param method. So you give it the string, and you tell it what interface that parameter uses, and you give it the address of an index that your driver is then going to use. The AsynPortDriver is basically computing these indexes for you and returning them. So the float64 method here, so this driver implements write float64. It gets passed an asyn user and the value. The function is going to be asyn user reason. And the first thing it does is to set the parameter in the parameter library. So it takes this value and calls set double param for that function, that was PASYN user reason, and sets the value. Now that's been set in the parameter library. And then it goes through some if statements saying if the function was update time, execute this code. If the update time has changed and we're running, then wake up the simulation task. So it calls epics event signal. Else, and then it does nothing. It says all the other parameters we don't need to act on immediately, so we just skip it. Then you do the callbacks so that higher layers see any changes that we made in the parameter library here. So here's just an example comparing writing a driver with AsynPortDriver to a driver that was written using the traditional approach. This happens to be a driver that was written out at Slack. I did this when I was teaching a course out at Slack on Asyn. So they had a driver for these Acromag IP440, IP445 digital I/O modules. And they had to, because they were using this traditional approach, they wrote a device support file. They wrote a header file that sort of defined the interface between device support and the driver, and then wrote a driver. And for this device, it was like 1,600 lines of code, and for this device it was 1,000 lines of code. I rewrote that using AsynPortDriver, and the whole, for the 440 it went from 200 down to 211 lines of code, 192 lines of code. So factor of 7 to 5 reduction in the number of lines of code with no reduction in capability. The reason that it uses much less code is we don't have to write device support. We use all the standard epics device support, so that gets rid of these two files. We don't need to define the interface between the driver and device support. That was most of what was in these header files. And there's lots of features that AsynPortDriver provides, like callbacks, that eliminates code from the driver because they had to do all that stuff in their driver. Additionally, we get these features. We can turn on debugging, and in the traditional version, you had to edit the source code, change a flag, recompile, and rebuild the application. Of course, with asyntrace, we can just turn on debugging in a standard way. We also get a standard way of getting a report out of AsynPortDriver that tells us most of the important stuff from AsynPortDriver without having to write that report code ourselves. Okay, so this is just sort of a summary of Synapse modules that currently use AsynPortDriver. Area detector, IP Unidigi, the DAC128V, measurement computing, we'll talk about this afternoon, the multi-channel analyzer, a few of the drivers. Not all the drivers there use AsynPortDriver yet. I haven't rewritten the Canberra driver, for example, but the struct driver, because I had to rewrite it recently anyway, I rewrote it in AsynPortDriver. The Quad EM, this is support for the APS and Electra CAN ELS Ethernet electrometers, the new Model 3 drivers for the motor package. And finally, let me just finish with some additions since 2012. Some of this will be familiar because it echoes stuff that's been added to Asyn, but some of it doesn't because it was specific to AsynPortDriver. There was no support previously to support the end of string operations on the Asyn Octet interface. Set and get the end of string terminators. Added new virtual methods for timestamp support, so your driver can implement its own if it wants, but there is a base class implementation for update timestamp, set and get timestamp. So the callback functions that do callbacks when you do call param callbacks now set the timestamp field in the callbacks. And change and the same thing basically for the array functions. So they also set the timestamps. An important thing is that if you've implemented these read functions in your driver, you also should be calling the method to update the timestamp so that you get this same behavior. Added support for the Asyn option interface. This is like for setting the baud rate on a serial port, that kind of thing. A new method to do flush octet. Before it was, you couldn't change the behavior of the flush method. Sometimes you need to, so you can implement flush octet. This is an important change that the length of the string parameters returned in read octet and octet callback is now the length of the string plus 1 rather than the length of the string. So the length, we put in a terminating null, nil, and we set the length to include that terminating nil character. There was some discussion on Tech Talk about this some time back, but I think this was the right way to do it. Change the meaning of the details argument to the report function. So the new meaning is if you set 0, you get no details. If you set it to 1, you will print the details for the parameter list 0. But if your driver has 16 addresses, it doesn't print the details for all 16 lists, which can be a lot of output. 2 prints it for all the parameter lists, and 3 prints the interrupt callback function, which is usually not so interesting. Sometimes it's useful. A few ideas of problems and future work. So AsynPortDriver was my first real C++ project, so I was only learning C++. So there's some real deficiencies in it, from a real C++ programmer's perspective. Most importantly, it doesn't use C++ exceptions. So you have to always check the status of the return from every function. And when you're setting a value in the parameter library, usually that's going to succeed, and so usually you don't check the status. But if something goes wrong, you'd really like to know. So that's a little bit clumsy. There's a number of other things that should be improved. For example, right now, there's not a way to force a callback even if a parameter hasn't changed its value. Usually that's what you want, but sometimes in a data acquisition task, you might want to have a callback going out that says that there's a new value even when it hasn't changed, so that people can be waiting for that new acquisition value. Right now you can force that because you can say set the value to its current value plus 1 and then set it to what you really want it to be. Then you're guaranteed that you will do a callback because it'll say it changed. But it's a kludge. There's too much code based on the existing class to change it in incompatible ways, but eventually there may be a new AsynPortDriver 2 class that will be better C++.